Okay, in this video, we're going to be doing Calc BC Problem Set number 9. The problems in a playlist are in the description below. Let's take a look at the problems. Number 1, we are given that f of x is 1 over the quantity 3x squared plus 14x plus 15. We want to find all x such that f of x is decreasing. All right, so first I'm going to, in my mind, rewrite this as that thing to the negative first so that I can just kind of chain rule it. So f prime is going to be negative 1, and then that thing, which is 3x squared plus 14x plus 15, to the negative second, and then times the derivative of that thing, which is 6x plus 14. All right, we got to rewrite this a little bit. What I'm going to do is I'm actually going to factor 3x squared plus 14x plus 15, just so we have like a better sense of what's going on here when we try to make a sign chart. So I'm going to say this is negative. That negative is crucial. Don't forget it. Negative. And then we have 6x plus 14 over 3x squared plus 14x plus 15 factors into 3x plus 5 times x plus 3. But since you're squaring the whole thing, you get 3x plus 5 squared, x plus 3 squared. What's key about that is that you will not have a sign change at negative 5/3 or negative 3 because they come from factors that have a multiplicity of 2. Any even power that you have there, you won't get a sign change. We got to do a sign chart. So negative 3 goes on, negative 7/3 goes on from the numerator, negative 5/3 goes on from the denominator. Take negative a billion and plug it in. You get negative in the numerator. You get definitely positive from the denominator because you're just squaring everything. But there's that negative hanging around overall. So you have negative times negative, that's positive. Negative 3, there won't be a sign change. At negative 7/3, there will be a sign change because 6x plus 14 is to the first power. And then negative 5/3, there will not be a sign change because that is from a second power thing. Or test points. It's up to you. I prefer to just use like properties of rational functions, but whatever way you like to deal with it, not a big deal. All right, now we just got to say where we're decreasing. So I'm going to say f of x is decreasing for negative 7/3 to negative 5/3 and greater than negative 5/3. I think you could also get away with just saying greater than negative 7/3, comma, x is not negative 5/3. I wouldn't really have a problem with that. But our reasoning is because f prime is less than 0 on that interval. All right, let's look at the next thing. We want to try to evaluate the integral from 1 to infinity of f of x dx. So this is an improper integral. Improper integrals require proper work. But we already know that this thing factors. So let's rewrite it as a factored thing. So we got this. You see something like this and you got to immediately in Calc BC think, this is definitely partial fractions. So let's do our partial fractions. So we have a over 3x plus 5 plus b over x plus 3. Now if you factored it into x plus 3 times 3x plus 5, then you would have a over x plus 3 and b over 3x plus 5. Your a and b would be switched, but our final answers will be the same regardless. So don't worry about that. All right, if we let x equal negative 5/3, we're figuring out what a is. So what you do is you go to 1 over 3x plus 5 times x plus 3, cover up 3x plus 5, and plug in negative 5/3. When you do that, you get 1 over, it's negative 5/3 plus 9/3, which is 4/3. So you have 1 over 4/3, which is 3/4. We'll do the same thing to basically find b. We let x equal negative 3, which means we're finding b. So you cover up x plus 3, you get 1 over negative 9 plus 5 is negative 4, so negative 1/4. All right, now proper work. So we can't have that upper bound be infinity if we're going to use the fundamental theorem. So what we do is we just kind of cheat and we say the limit is b approaching infinity, 1 to b. Plug in your values for a and b here. So we have this. You know you're going to get natural logs. Anytime you do partial fractions, you're definitely getting natural logs. Sometimes you also get arctans. But you definitely get natural logs. All right, these are pretty straightforward. So we get the limit as b approaches infinity. So for this one, there's a 3/4, but do not forget the chain rule. People forget it all the time, or u substitution, however you want to think about it. There should be a 3 in the numerator because u is 3x plus 5. So a 3 in the numerator, a 1/3 on the outside. So you have 3/4 times 1/3 is 1/4. Natural log, don't forget your absolute values, like this. And then minus 1/4, this one's straightforward, just natural log absolute value of x plus 3. Now what you want to do with these, we have to evaluate from 1 to b. If you have natural logs, it is, I would say, always the case, but I'm going to say almost always the case because I'm not sure if I'm not thinking of a particular thing here. it's almost always the case that you want to rewrite it using properties of logs before you take the limit. So what I'm going to do is I am going to do the limit as b approaches infinity. So we'll have 1/4, and then we'll have the natural log of, since we're going to infinity, we don't really need the absolute value anymore. Also, I definitely should have changed those x's into b's at this point, but I forgot to, and I don't want to go back and change it, so I'm not going to. So we have the limit as b approaches infinity, 1/4 natural log of, read it like this, 3b plus 5 over b plus 3. And then when I plug in 1, I just get, so it's minus 1/4, the natural log of 8 over 4. So it doesn't have b in it, so it doesn't need to be inside the limit. When I take the limit as b approaches infinity of 3b plus 5 over b plus 3, I definitely just get 3. You could use L'Hopital's on that. I don't think you really need to. So we have 1/4 natural log of 3 minus 1/4 natural log of 2. You could leave your answer like that. I think that would be okay. But multiple choice options, they'll always simplify. So this property of logs is subtraction between them becomes division within. We actually use that on the previous step as well. So we have 1/4, the natural log of 3/2. That's our answer. All right, let's look at the next part. Apply the integral test to determine the convergence or divergence of the sum of from 1 to infinity of f of n. All right, we already did all the work for this, basically. So we know that f of x is positive, because if you're plugging in positive numbers, you're always just getting positive. So like we don't have to wonder about that. Continuous. We know that the only problems occur at -3 and negative 3/5, I think it was, or 5/3, one of those. But anyway, they're negative values, right? So everything greater than 1, definitely continuous. And then we also know we are definitely decreasing for x greater than 1, because we had to show where f of x was decreasing in part A. So we'll say, and decreasing for x greater than or equal to 1. So we already did all the steps, so we don't have to worry about that so much. And then we also know, because we did the work, that the integral from 1 to infinity of f of x is 1/4 natural log of 3/2, which means that this integral converges. And if the integral converges, then we know that the series converges by the integral test. So we did all the work ahead of time. All right, that's a pretty good problem. You should be on the lookout for that with series problems in particular. If they're making you go through like, where are the discontinuities? Where is this thing decreasing? And then suddenly there's a series, it's probably the case that you're using the integral test, or you can at least. Now on this problem, if I just threw it at you and you weren't thinking integral test, you almost certainly would have thought limit comparison test, because this is essentially a p-series that's just kind of like shifted around a little bit. So we are going to say, I mean, it's basically just 1 over x squared or 1 over n squared. That definitely converges because p is equal to 2, which is greater than 1. So we now are going to find the limit of the nth term of one of them divided by the nth term of the other. So we will find the limit as n approaches infinity, 1 over 3n squared plus 14n plus 15 all over 1 over n squared, which I'm going to simplify a little bit. Usually I wouldn't simplify this, but only because we already know the answer. Like they're not contrived. I mean, these are legitimate problems. But you kind of know the answer going in because of the choice you made for your p-series. Like I chose 1 over n squared. I'm guaranteed to get 1/3 at this point. If you flipped it up and you put 1 over n squared in the numerator and the other series in the denominator, you just get 3. That's fine, because the criteria for convergence or divergence, the criteria here for doing the same thing is that you get a positive finite number. Both 1/3 and 3 are positive and finite, so it wouldn't make a difference. Positive and finite, since you get that, they both do the same thing, which means that the sum from 1 to infinity of f of n converges by the limit comparison test. So you could use limit comparison there. I think a lot of people would. I think almost everybody would, to be honest. All right, let's look at the next problem, which I think is the last problem on this set. Given y equals f of x is the particular solution to dy dx equals y squared over x plus 1 with y of 0 equals 2. We want to approximate y of 2 using the line tangent to y equals f of x at x equals 0. 2 is so far from 0 that this feels like an invalid thing to do, but we're going to do it anyway. All right, so to do this, we need to know the value of the derivative at 0, 2. So dy dx evaluated at 0, 2 is just going to give us 4 over 0 plus 1. So 4 over 1, which is 4, which means our tangent line is y minus 2 equals 4 quantity x minus 0, which means that y of 2 is approximately 4 times, 2 plus 4 times 2, which is 10. So that's our approximation using a tangent line. We can also use an approximation from a second degree Taylor polynomial centered at 0. But for that, what we're going to need to do is we're going to need to find the second derivative. So let's start off doing that. So the second derivative is going to be, this requires a quotient rule. So it's bottom, which is x plus 1. Derivative of the top is going to be 2y dy dx by the chain rule, minus top, which is y squared, derivative of the bottom, which is 1, all over the bottom squared. And again, we're going to evaluate it at the point 0, 2, where we know that dy dx is 4. So it's going to be 1 times 2 is 4, dy dx is 4, minus 2 squared is 4, so many 4s. We get 16 minus 4, which is 12. All right, let's write the second degree Taylor polynomial at 0. So to do that, I'm going to say f of x is approximately the value at 0, which is 2, plus the first derivative, x minus 0 to the first over 1 factorial, plus the second derivative, x minus 0 to the second over 2 factorial. That's our polynomial. You have to memorize that. That pattern is, you're going to use it so often. And now we just need to approximate it 2, so we'll say f of 2 is approximately. You'll notice this is just the tangent line plus another extra term. That's a fact. The first degree Taylor polynomial is the tangent line. So we get 2 plus 8 plus 24. So it gets big. So we get 10 plus 24, 34. So our approximation with the tangent line is 10. With the second degree Taylor polynomial is 34. You know, it'll just keep changing if we keep using a higher degree polynomial. But anyway, that's the problem set. I hope this was helpful, and good luck.